All right. Okay, so I'll also turn my camera on.
Great.
All right. Sorry, I had to find the button. Gotta zoom.
We can see you now.
All right.
Cool.
All right. So hello, everyone. My name is Andrew Harris. I'm a fourth-year computer science undergraduate from Memorial University in Newfoundland, Canada. It is currently almost 8 p.m. over here, so it's completely dark outside. But yeah, I'm here to talk about Sarracen. So Sarracen has been a collaboration between me and Dr. Tricco I had a research term last summer, and then I worked on it more this semester. And what it is, it's a Python tool, which is able to seamlessly read in phantom binary data and produce visualization and analysis, kind of like what you see on the right side here. This was produced entirely in Sarracen. So it's capable of doing interpolation for line plots or 2D images. And as well, it can also do very easy scriptable filtering and analysis of data. So you can create derived values, go ahead and, like, if you want to only render particles with certain properties and such, it's all very customizable. Like this figure that's here, you can change all the labels, you can set titles, change color schemes, and do a lot of very complicated things. So because we're using Python, we have a couple of benefits that come from that. So you can very easily modify the output. Like I said, you can do scriptable analysis and such. And as well, Python has a really large library of scientific and mathematical tools that are available. So if anyone here has ever seen NumPy or SciPy, you can integrate that directly into your SPH analysis with Sarracen. The library itself uses matplotlib and pandas kind of under the hood. So if you've ever used those libraries, you'll have a very easy time getting used to how Sarracen does things. So as well, on the left, you can see this is a screenshot of a JUPYTER notebook, which is kind of a web-based document and code. It's a place where you can have documents and code together. And so it allows you to do some very nice visual presentations of SPH data. And you can run them locally, or you can have a remote machine for it. So yeah, the instructions to install Sarracen, we're hosted on PyPy. So you can just use this pip command in order to install the library. And you can import it into your code with this command. The source code is completely available at this GitHub address. And there's full documentation at this Read the Docs website, which includes an installation guide, simple to harder examples, and a full API that you can reference. So one of the concerns when making this library work was that SPH interpolation is very expensive if you're doing it over millions or even more particles. And Python, it's high level and it's generally not known for being super fast in those kind of circumstances. So we took a few steps to mitigate this as much as we could. We used a library called Numba, which for each of the really heavy interpolation functions, it goes in beforehand and compiles it into really fast machine code that can run in parallel. And you end up with a very nice CPU usage over multiple cores. And so this compilation, it happens just in time. So the first time you run any function, there'll be a bit of overhead as it compiles it first, but then it's cached afterwards. So any other time that you use that, it'll be much faster. As well, Numba also supports GPU code. So all of the interpolation functions can be ran on a dedicated graphics card that's CUDA enabled. And generally, in my experience, you get much better performance off of the GPU rather than the CPU. So I'm sure many of you in this room have used Splash before. And so Sarracen does cover a lot of the same domain that Splash does, but we kind of intended it to complement Splash rather than replace it. So Splash is generally, it's much faster than Sarracen. Because I mean, it's Fortran super fast machine code, so it's very hard to beat with Python. And as well, Splash has a very nice interactive mode where you can go through and get a really nice initial exploration of your data set. Sarracen really comes into its own when you add more complexity to your analysis. So if you're making like a pipeline of analysis and such, and you want plots that you would, in Splash, you would have to make a Fortran routine in order to run, that's where Sarracen really comes in handy. So I actually have a Jupyter notebook over here that I'm gonna pull over and just do a live demo of Sarracen. So can you see that website right here? All right. So this is a Jupyter notebook running live on my machine. So to start off, I'll just import Sarracen with that command I had in that slide earlier. And generally, when you're using Sarracen, you want to have some other libraries included. Specifically, matplotlib is very useful to have because that kind of unlocks a lot of functionality with the plotting. So yeah, right here, I have Hydro 256, which is a raw phantom binary dump that's at this location. And if I use the read phantom function, I can load this data into a Sarracen data frame, which is similar to a pandas data frame if you've used that library before. And it loads all the particles into this table where you have all the values of each particle as columns and just all of the particles as rows. And so with this Sarracen data frame, you can do some very nice analysis just with this alone. For example, there's SDF describe, which if you run that, it'll just compute some basic statistical measures of the data set. Just let that run. And yeah, you get like the average values for each column, you get the standard deviation, quantiles, minimum, maximum, and you can get into much more complicated functionality there. So if you actually want to render something with the library, the key rendering function is as that Sarracen data frame.render. And I'm just going to render the density here with the row keyword. And this will produce a column interpolated plot, meaning it's integrated along the z-axis. And so I run that through. This is that just-in-time compilation coming in where it's taking a little longer the first time. And yeah, that is a basic column rendered plot produced with Sarracen. So if you want to change some things about this plot, you notice that you can't really see a lot of the detail in these darker regions. So I'll put that on a log scale instead. And then let that run. And so yeah, there's a whole lot of options. I can't cover them all here, but I'll just do a few of them. Yeah, you can see that you get more detail in this region. It's all on a log scale. And if instead of doing a column render, you want to do just a cross-sectional slice across the data, you can use the cross-section argument. The Z particles here, as you can see up here, go from approximately 0 to 1. So I'll do a cross-section right in the middle. And yeah, that'll just only take the particles that are at that halfway point. So I said earlier that having matplotlib imported is useful because here we can make a axis object and we can pass that into the render function. And so this axes object contains all the information about the plot. And so we can change things about it, like set the title, for example. And as well, I have a GPU in my machine, so I'm using a GPU to produce this plot. And yeah, you can see I just changed the title to have hydrodynamic turbulence. But you can change all the labels this way. You can change a whole lot of properties about the overall plot. So one thing that Sarracen manages to do pretty well is handle the vectored information. So I'm going to load the Orszag-Tang vortex data set, if you've seen that before, but with magnetic field as a as a vectored value. So just like before, I'm going to make an axes object, and I'm going to render density on the bottom, but then on top, I'm going to do a streamline plot of the magnetic field. If I run that, it produces this plot, which I think it looks pretty cool. Yeah, so I'll do a much more complicated example down here. This is a dusty disk data set, which is important about this is that it contains dust, gas, and sink particles all together. So Sarracen can deal with this in a couple of ways. The default behavior, which I just have defined there, is to split the particles into two different data frames, one for dust and gas particles, like all the normal particles together, and one just for the sink particles. So if I do that, you can see that all of the gas and dust particles, I type 1 and 7, are in that first data frame. And then the sink particles just go into the second one. There's only 3 of them here. You can change it so the types are separated into all different data frames. So there'd be 3 for this, but usually this works pretty well. Yeah, so one thing that's nice is because we're so integrated with pandas, you can very easily create derived values in your data set. So here, you can just define an operation on each individual column. Here, I'm just doing a radius calculation, just something simple. And then if I do that, pandas just deals with all of the complexity of doing it over each row. And there we have the radius calculated for all the particles, just that easy. So kind of putting it all together to a more complicated example. Here is one where we actually create 2 axes objects side by side, and then we'll draw only the gas particles on the first one, and then only the dust particles on the second one, and just do a scatter plot of the sink particle positions on top of those plots. And then if I run that.
Andrew, you have 3 minutes remaining.
All right. Yeah, I'm almost done. Yeah, and you end up with this plot. So that's kind of where Sarracen really comes into its own, is when you get the escalating complexities of plots with several layers, multiple plots in a certain arrangement and such. So yeah, there's a whole lot you can do with this. So yeah, that is Sarracen.
Thank you. Does anyone have any questions for Andrew? My question, Andrew, is we can download it now, right? We can use it now?
Yes, it is usable now.
Cool. Can people make contributions to the code as well? Like if somebody finds something particularly interesting they'd like to add, can they, add it?
Yes, I believe it's all public. The GitHub's open. You can submit pull requests. It's all open to use.
Just a comment and a question. I think the comment is you've done a fantastic job. Question is just on the GPU mode. Is there a reason why the GPU mode is not default?
So the reason that I had for that is there's a lot of cases where, well, when we were originally building it, we were converting some of it to use GPU mode. There were some functions that just didn't have that backend, so being able to switch between them was nice. But as well, if you're running on a machine that doesn't have a CPU, or specifically if it's not CUDA enabled, because sometimes setting that up is a little bit of a headache, being able to just have something that works 99% of the time as the default was just, we thought that was a good idea.
I guess the question would be more, could you do like a try and then fail thing? So if it found the CUDA libraries and it found the GPU, it would just use it. And if it wasn't there, it would revert to CPU.
Yeah, I like that. Yeah, I'll see if I can do that. Yeah.
Cool. Sounds like a good issue to raise on the GitHub.
Yep, I'll open up the GitHub here. Yeah, so we have this, and you can submit issues to this page, and we'll get to it when we can.
Sarracen is linked from the Phantom documentation.
Hello. Can I make two questions? Yeah, sure. First, Andrew, great work. The first question is
you.
how you make a performance test of, let's say, a render of a particular image against Splash and see how fast is the rendering time.
I've not done, the only comparison performance tests I've done between them has mostly been observational at this point, because I can do that kind of performance test over time in Sarracen quite easily, but I'm not sure how to do that in Splash with the timing specifically. But yeah, that is something that I would love to have just to have as a performance benchmark. Yeah.
Okay, and the second question is more specific about the code. Is there some kind of function or command in which you can make like a sets of figures in which you make, I don't know, like a zoom in X and Y, or changing the color bar or stuff like that?
So you mean having multiple plots together, being able to change individual?
Yeah, like a series of figures that is being generated automatically, let's say 100 of them, in which you are making a zoom in or zoom out.
Okay. Well, with this, I kind of showed down here having 2 of them. I could expand that to have 4 subplots, and I'm sure you could expand that to make 100, like 10 by 10 if you want. And yeah, it has all the normal Python functionality, so you can make it you can fill in the plots for across the grid. Yes.
Yeah. All right. Thank you.
Hello.
Yeah, just to add to that, like, sorry, all of this is scriptable. So if you want to make 100 plots, you can make a for loop. If you're looking to make animations of multiple files, there's no out of the box way to do it in one line, but put that in a for loop, read each file, make the image.
Yeah, specifically.
Sorry. Yeah, I was thinking about that, but I was wondering because sometimes sometimes it's just I was wondering if you have a inbuilt function for that, but if not, that's good too. Thanks.
Hi. Is there anything in there to model or to show any plots about orbital evolution or mass transfer or what is happening to the sync particles?
I think I have to bring that to you, Dr. Tricco.
Yeah, I guess it kind of ties in a bit right now is that the way the code is structured is reading in one dump file at a time. So we don't really have, it's a little bit clunky to do stuff over time, which right now would mostly be scripting it by hand of making a for loop, reading each file and sort of handling that yourself. It's definitely on the roadmap, but it's not there right now.
Okay, good. Maybe by reading in the evolution files, the .ev files. Because we also made some sort of pipeline ourselves, but it's much slower, I guess, and not as good. So it would be nice to use yours, but we also need that kind of plots. But maybe we can like work together on that. I don't know. We can also implement those in your pipeline. But thank you. It looks nice.
Yeah, it's a conversation I want to have with Daniel as well about potentially changing the EV files to just use a regular CSV, because then you can, there's a lot of out-of-the-box tools for dealing with CSVs. But that's a longer conversation, I guess.
Hi, Andrew. Very interesting talk. I usually use Plonk to analyze the simulation and to generate figures and to analyze the data. But I was wondering, what would you say is the big difference compared to Sarracen? Because for me, it looks very similar to what I usually do with Plonk. So it's a big difference, or it's like a complementary package?
I haven't had a whole lot of experience with Planck to be able to speak on that. I apologize, but
yeah, okay, no problem.
Yeah, I mean, I can add some bit there. Just I'm not sure. I could be mistaken on this. If Plonk is under development still, or how much development is going on with it. Where our intention is to keep Sarracen maintained for the long-term future. And as well, we're using pandas as our backend for handling data, and there's a lot of advantages using pandas, which sort of Andrew has outlined here.
Yeah, I can also help to answer that. So the main limitation of Plonk is it wouldn't read this files directly. So you have to do either have convert to HDF5, or you have to compile Phantom with HDF5, which is something that keeps breaking. So this just reads, the main difference is just works straight from the binary snapshot.
Mhm. Yeah.
Thank
like
you very
this,
much, Andrew. Sorry, go ahead.
Yeah, it's this read Phantom file. It works directly with the Phantom dumps. Yes.
Cool. Thank you very much. And thank you for your presentation and for staying up late, both you and Armina for staying up late. So thank you very much.
All right.
And our final speaker for the session is Ellie. Are you able to share your screen now?
I will see.
What?
Thank you.
Perfect. Andrew, I think you need to stop.